we are talking about grade 8, specifically the geometry standards. Students need to understand congruence, similarity using physical models, transparencies, or geometry software, understand and apply the Pythagorean theorem, and solve real-world and mathematical problems involving volume of cylinders, cones, and spheres. Find a way to partition a regular hexagon into two congruent figures. Explain how you know the two figures are congruent. So if we start with a regular hexagon here, there are multiple different ways that I could split it into two congruent figures. Particularly, I could split it as I have pictured, or split it in any other one of the vertexes. We could draw a line through opposite vertices to divide the hexagon into two congruent pieces. Each side results in a trapezoid, and if we were to make a reflection across the line that we drew, the line takes one trapezoid to the other. Find as many ways to partition a regular hexagon into two congruent figures. So here's one option, just slightly off-skewed, and we could rotate this and continue the same type of pattern. Here's another one, and yet another one, and a final one. Note that there's an infinite possibility of ways that we could partition into two congruent figures. So in each case, the figures were constructed so that 180-degree rotation about the center will line them up one on top of the other. Find a way to partition a regular hexagon into four congruent figures and explain how you know the four figures are congruent. So let's say I take my hexagon and I cut it in four. And here I used isometric paper to do that, and then I colored them. If we consider the vertical and horizontal lines as the lines of reflection, the yellow region is the image of the red region when we reflect across the vertical line. So these two red regions are congruent. The green region is the image of the blue region when we reflect across the vertical line. So those two regions are congruent. Further, the yellow region is the image of the green region when we reflect across the horizontal line. So those two are congruent. And so all four regions are congruent to one another. Find a way to partition a regular hexagon into 8 congruent figures. How do you know the figures are congruent? So here I've partitioned using the same isometric paper into 8 different trapezoids. We can show they are congruent. Let's start with the vertical line. That kind of splits it down the middle here. All four regions on the left of that vertical line are congruent to their mirror images on the right. We can show that the purple and orange regions are congruent if we were to draw another vertical line directly down the left side here. We could show that these two are congruent if they reflect across that line. Further, if we were going to rotate a multiple of 60 degrees around the center piece here, all 8 regions would also be congruent to one another. Translations slide objects, rotations turn objects, and reflections flip objects. Image A and image B are both rotations of the pre-image 1, yet they look different. How can we describe the rotations? Let's start with going from the pre-image 1 to image B. I see that if I were to tip my pre-image clockwise, I would be able to describe the direction. Further, if I were to tip my pre-image counterclockwise, I would be able to describe the direction to image A. I can also say that the degree of my rotation was 90 degrees. So ultimately, we had a 90 degrees clockwise rotation to obtain image B, and we had a 90-degree counterclockwise rotation to obtain image A. We can also describe reflections, but first we need a reflection line. So let's start with line 1. I can see that if I were to reflect over line 1, I would obtain object C prime. Further, if I were to create another line for a reflection, let's call that line 2, I can flip from C prime to C prime prime and reflect over that as well. So we had a vertical flip from image C to image C prime, and we had a horizontal flip from C prime to C prime prime. The arrow below is rotated 90 degrees counterclockwise. Draw the image of the arrow after the rotation. Pause the video and see if we can do that. Your image should look like this one, rotated 90 degrees counterclockwise. Transformations preserve side length and angle measurements. Describe the transformation and fill in the missing labels. Which is the pre-image and which is the image? How do we know? The transformation is a horizontal reflection. So therefore, B and B prime are equivalent, C prime are equivalent, D prime, E prime, A prime are all equivalent. The pre-image is the blue shape, since the pink image is labeled with the prime notations. That is our indication that we have a new image based on our pre-image. Polygon ABCD is translated as shown. Which angle is congruent to angle B? Take a guess. Did you guess S? That is correct. Triangle DEF is rotated 180 degrees to form triangle HIJ. Which angle is congruent to F? Angle J is congruent to F. When figures are rotated, reflected, or translated, the images are congruent. Determine which images could be made by rotating, reflecting, or translating pre-image A. Pause the video and circle all those you think are correct. All the circled items can be created using translations, rotations, and reflections. They are congruent. Triangle DEF undergoes a vertical reflection. What is the length of ED? The length of E prime D prime should also be 4 millimeters. We know that it does not matter if it's rotated, reflected, or translated, images stay congruent. Which of the following transformation preserve congruence? Rotations, reflections, translations, all of the above, or none of the above? As I just stated in the previous slide, all rotations, reflections, and translations preserve congruence no matter which of the combinations above happen. Tell what is missing from each transformation's description. The green square translated right, but not up or down. The cupcake rotated 90 degrees about the origin. The blue plant was reflected in a slanted line. They're not very specific. The translation is missing the number of units the figure has shifted. So the green square was translated right, but it doesn't tell us how far right we need to go. The cupcake is rotated 90 degrees about the origin, but which direction was the rotation? Counterclockwise or clockwise? The blue plant was reflected in a slanted line. However, what specific diagonal line was the figure reflected over? It's not very specific. So we can't just say the obvious what had happened. We need to be specific with how it happens. Georgia made a painting in a coordinate plane. While it was still wet, she folded her paper along the y-axis, resulting in the image shown here. Then she folded it again along the x-axis, making a new image. What did her original painting look like? And what does the last image look like? When she folds the paper, they make reflections of the painting as follows with the dashed lines. With this, we see the orientations are reversed. However, the corresponding parts are the same distance from the lines in which they were reflected. We know the result of the transformation in the coordinate plane is always a figure congruent to the original. Jim drafted 2 copies of a logo in the coordinate plane. He wondered if the final logo was congruent to the first. Robbie said it wasn't, and Jim said it was. Who do you agree with, and explain? We know that if we have a series of transformations, we can prove 2 figures are congruent, just as if we had a single transformation. So let's say we rotate clockwise about the origin 90 degrees. So now we have lifted it this far. The image is still reversed, so let's try a reflection across the y-axis, which would make it look like this. So now it's the correct direction. However, one more transformation is needed to get us to the last image. We would need to go right 2 units and down 1 unit. Quadrilateral ABCD is a trapezoid where the lengths of AD are 15, AB is 50, BC is 20, and the altitude is 12. What is the area of the trapezoid? The first thing I notice is that I can draw a vertical line from point A down to the line CD such that it creates a 90-degree angle. Same with drawing a vertical line from B down to CD, such that that also creates a right angle. And both of those distances will also be 12. So then I can find the smaller lengths of the legs of my right triangles as follows. Giving me 12 squared plus B squared is 15 squared. Or 144 plus B squared is 225. Subtracting 144 from both sides, B squared is equal to 81, so the length of this leg is 9. Following the same pattern for the other triangle, I will have 12 squared plus B squared is 20 squared, or 144 plus B squared is 400. Subtracting 144 gives me B squared equal to 256, and the square root of 256 is 16. So the length of this leg is 16. We have 2 different options that we could use. We could decompose our trapezoid into 2 triangles and a rectangle and add their areas together, since finding the area is additive of composite functions or composite shapes. So the area of this trapezoid could be the area of the triangle on the left plus the area of the rectangle plus the area of the triangle on the right. That would give us half times base of 9 times 12 of height, plus the area of the rectangle, 50 times 12, plus the area of the triangle on the right, which is half times 16 times 12, giving us 54 plus 600 plus 96 for a total area of 750. Or we could use the area of a trapezoid formula, which is half times height times the base 1 plus base 2. So half times the height of 12 times our base of 50 across the top and our base of 75 across the bottom, which is 9 plus 50 plus 16, giving us half of 12, or 6, times 125, which also gives us 750. Let's use the Pythagorean theorem to help us find the distance from point A to point B. Notice this is a diagonal length crossways, so we're going to need to find some information. First, we need to find the distance from point B to the corner point C that we label, so that we can create a nice right angle. But in order to find length B to C, we need to use the triangle that's listed there and find that length B to C. I know that the bottom base is 12 and the other leg is 5 yards. So using the formula 12 squared plus 5 squared equals x squared, we get 144 plus 25 equal to x squared, or 169 equals x. Taking the square root, I see that x is equal to 13. So now that we know the base of our right triangle, we can use this now to identify the length of A to B with our new triangle that we have. We know that the bottom leg is 13. We know that our height of this triangle is 84. We need to find the hypotenuse. So 13 squared plus 84 squared is x squared. 169 plus 7,056 is x squared. 7,225, if we take the square root of that, we see that the length from A to B is 85 yards. We can extend our ideas of finding the volume of prisms to finding the volume of a cylinder. We know that the volume of a prism is base times height, where B is the area of the base that we're looking at, and H is the height of the object. The volume of a cylinder is also base times height, where B is the area of the base and H is the height. Except this time the area of the base of a cylinder is a circle, so we need to know the formula for the area of a circle, which we know is pi r squared. The base, or the area of the circle, is 3.14 times our radius of 8 squared, giving us 296 meters squared. We now need to take that times the height of our cylinder, which is 10, for a total volume of 209 6/10 meters cubed, since we're in volume. A cylinder has a diameter that is 8 inches long and a height that is 2 inches tall. What is the volume? So we first need to know the area of the base. So we need to know the area of the circle that it's in question. So 3.14 times the radius. Now it gives us the diameter. We know that the radius is half of the diameter, so 4 squared, giving us 50.24. Now we can take the area of our base and multiply it by how tall it is, which is 2, giving us 148 thousandths inches cubed. We can extend our ideas of finding the volume of a cylinder, finding the volume of a cone. The volume of a cone is 1/3 the area of the base times the height. So find the volume of the cone rounding to the nearest thousandth. The area of our base is still the area of a circle, so pi r squared. So 3.14 times the radius of 2.7 squared gives us 22.89. We need to take that times 1/3 and times the height of this cone, which is 4 3/10. Multiplying them all together, we see that we get 32 81 inches cubed. We can further extend our ideas of finding the volume of a cylinder to find the volume of a sphere. The volume of a sphere is 2/3 the volume of a cylinder. So if we know that the volume of a cylinder is pi r squared times height, and in particular our height here is 2r, since radius is just halfway and 2 radiuses would be all the way across. We can combine like terms and multiply or rearrange. Multiply our whole numbers to give us 4/3, and our radius squared times radius is radius cubes. So therefore the volume of a sphere is 4/3 times pi times radius cubed. So let's find the volume of this sphere here, which is 4/3 times 3.14 times the radius cubed, or 5 cubed. Multiplying all together gives us 523 3/10 centimeters cubed. Find the volume of the hemisphere. Well, a hemisphere is half the volume of a sphere. So therefore, the volume of a sphere is 4/3 pi r cubed. We want half of that, so half of 4/3 pi r cubed, giving us 2/3 pi r cubed as our formula. Plugging in 3.14 for pi and 2.1 for radius, we see that this would be 19 4/10 centimeters cubed. Complex volumes can be found by identifying the figures and adding their volumes together, because adding volumes or finding the volume of complex shapes is additive. A grain silo is designed as a cylindrical container that has a cone-shaped bottom so that it empties easily. If the silo is filled all the way to the top, how much grain by volume is it holding? So we have the volume of a cylinder plus the volume of a cone to identify the total volume altogether. So our total volume would be the volume of a cylinder, pi r squared h, plus the volume of a cone. So plugging in the information particular to the cylinder and the cone, we get 3.14 times the radius of the cylinder, which is half of 18 or 9, times the height of the cylinder, which is 25, plus 1/3 times pi 3.14 times the radius of the cone is also 9, except the height of the cone is 10. Simplifying, we see that we end up with 6,358.5 plus 847 8/10. Adding them together, we see that we get 7,206 3/10 feet cubed.